All right, good morning, everybody. Can I just get confirmation that you can hear and see me?
Hi, sir.
Welcome to the actual last class.
Heard that one before. Not going to fool me today.
I know, I know. Well, you can always show up for office hours and never end. But this will definitely be the actual last lecture, and I'll put it in the announcements that after today, but for every day, Monday to Friday, until our final exam, we'll have office hours. I don't know if we need that much. 9:30 or 10:30, which one is better? If we just have an hour every day, is 9:30 or 10:30 better? Immediately mixed results. I feel 2 hours a day is a little excessive. I'm just going to sit here with no one showing up. We'll think about it. Or should we meet in the middle and make it 10? Well, you can think about that, and we have to have the last quiz before we can talk about the final exam. So we need to see what did you like on the last quiz after we do it, what did you not like. Otherwise, we can't really vote on what's in the final exam. So let's get that last bit out of the way, and we're going to talk about volume. Volume is the last little concept. And I say little because we're not going to go crazy with formulas uh, and such. We're going to just get the volume concept. Now, just like we have a little unit square that we're trying to count how many of the unit squares can fit into an area or a region, giving me the concept of area. For the concept of volume, I have a little 1 by 1 by 1 cube, whatever the units may be, and I'm trying to see how many of that unit cube can fit into a volume, a shape, a three-dimensional shape. And that gives us the concept of volume, which is a natural extension of the length and area concept. So the main thing when it comes to elementary school is, and volume of three-dimensional shapes, is the concept of a prism. Now, we've seen prism before, but this does not necessarily mean not necessarily regular. It can be other kinds of prisms as well, but I still have some shape for my base. Doesn't have to be regular. The concept of a prism is still the sides go straight up, perpendicular to the base, and I have the same shape at the top. The same shape as the base is at the top again. So let me finish my sketch. Oop, that was too low, too high. The more we practice this, the better we get, it seems. So whatever the base shape is, it doesn't even have to be a polygon. I get the same shape at the top, and all these sides are perpendicular to the base. Or for example, I can have a circular base. And then all the sides go straight up, and I have the same circle at the top. let me fix that. So here we have a, oops, here we have a circular prism. Here we have maybe an irregular hexagonal prism. It's still based on what that base shape is. So the concept of a prism is definitely important for elementary school level when it comes to three-dimensional shape, and it can extend a little bit further than a regular prism. So when we talk about volume, there is, I guess, a formula, if you will, but it's more a formula in words. The volume of a prism is simply going to be the area of the base times the height of the prism. So here I have the height. Here I have the height. So I simply need to know how tall the sides are and the dimensions of the base, and then I can have the calculation for the volume of a prism. Area of the base times the height, which I think most people knew already. So now it is just a question of why my polar bear is not looking correctly. Okay, anyway, it's just a question of seeing some examples and practicing this half formula in words. So let's zoom in here zoom on exercise 17.6. Draw, oh, that's good practice, and calculate the volume of the following regular prisms. So we have a triangular prism with side length 2. Triangular prism, side length 2. So it's regular, so they just give me, so all the sides are the same, just to make it simple. Exercise 17.6. Exercise 17.6. Let me give you a minute while I'm trying to fix my polar bear, and you can see if you can draw the triangular prism. Hmm. Polar bear will need a reset, which I don't necessarily want to do right now. Oh well, we'll just have a comic relief polar bear. So triangular prism, so I need to draw a triangle. You can make it as big or as small as you want. Whoops, let's at least try and go perpendicular straight up. Like so. And yeah, the back ones are dotted lines, but it's okay. Let's make them a little dotted. There we go. And my side length, they said, was 2, whatever the units are. Let's make them centimeters, just to see a unit. So now I need to calculate the area of the base, and that is an equilateral triangle, side length 2. I don't have the height of the triangle, so maybe the general regular polygon area formula might be simpler. side length 2 squared times n, the number of sides of the triangle, over 4 times tan. This formula is going to haunt us. 180 degrees over 3 again. Now, luckily, this is a 4 and this is a 4, so that cancels, making it a little bit easier. 180 degrees over 3 is 60 degrees. So we get to practice that wonderful formula again. And we get, for the area of the base, 1.7321 if we round it. So then the volume of, or just the volume of the shape, is going to be 1.7321 times 2. So let's just get units here. Here we have an area, so that's square centimeters. Here we're going to have the square centimeters times 2 centimeters will give us an answer in the unit for volume, which is cubic centimeters. So we take that, we times it by 2. Just have enough decimals so that when I round it to 2 decimals, I know those two are correct. And we get 3.46 cubic centimeters. How do we feel about volume of a prism?
Sounds good to me.
All right, so no intimidating formula here, except the one that we have seen before. So let's look at the other ones. Square prism. What is another word for a regular square prism? Oh, I did not even finish my question. A cube. With side length 3. So we have our cube, which I will do super fast. That looks very uncube-like. 3, 3, all the way around. So in this case, the volume is quite straightforward. It's 3 to the power of 3. 3 times 3 times 3. Because the square base has area 3 times 3 times another 3. Because it's a cube already, I get 27. They didn't say the units. Whatever the units cubed. So in the simplest case, square, cube, those are uh, much easier than any formula I really need to remember. But we can practice a pentagonal prism with side length 4 because I need to practice. Now I'm going to try and make my pentagon maybe go a little off center here. See if that, oh, that's way too upright. I want to lay it flat. I don't know, something like that. And then I go up along the sides. It's not going to be very big. And maybe make some dotted lines. There we go. Okay, so now I have side length 4. It's regular, so all the sides are 4. So my area of the base is going to be side length squared times number of sides of the pentagon is 5. Let me make it clear, 5 over 4 times tan of 180 degrees over 5. I can simplify that, or I can just type it in just as is. Your choice. Let's do that. Did MathBot dislike what I did there? Why? Why, MathBot? Why? Why did you not like it? Just like before, the formula is complete overkill for the square. I did the formula for the square. It's the area of the base is 3 times 3 times the height is 3. So 3 times 3 times 3. So we did do it. We just didn't need a fancy formula when it's a square. Why is MathBot unhappy? 16 times 5 divided by 4. It doesn't like that way I did it. That is how you could do it on a calculator though. Let's see. Nope, it is unhappy. So can someone give me the answer, please? Maybe it doesn't like calculation inside of the tan function. That could be, that's my guess. So for just the area of the base, right? Just the area of the base, 27 point, oops, 27.527. So then the volume is that area times 4, which MathBot should not have a problem with. Yeah, I'm guessing it was something with the calculation inside the tan function. It did not like 110 point, let's say 11 if we round to 2 decimal places. And because we started with more, we have fairly good confidence that our 2 decimals are correct. All right, so we practiced some drawing. We practiced, um, I guess it could be a new formula, but hopefully most of you knew the volume formula for this basic three-dimensional shape, the prism. Yes, in elementary school, you won't um, make the base too fancy because we don't want them to see the general formula for the area of a regular polygon, but the concept of a prism is still there. Let's just practice one that should be in there, and that is for a cylinder or a circular prism. So let's say I have a circular prism or cylinder, call it whatever you want. Like that. Oh, so close. And let's say we have a radius, let's say 2 centimeters, and we have a height, let's say 5 centimeters, and that's all we need. So then the volume is going to be the area of a circle, which is pi r squared, times the height 5. Pi r squared, so I have pi times 2 centimeters squared, and that will give me my answer. So I seem to get 62.83, and that would be cubic centimeters. So if they give me the unit, then I'll uh, use the unit in my answer, but sometimes they do, sometimes they don't. All right. One thing I want to mention that is not in the book, and I don't, well, I know we're not going to waste a question in a test on this, but it does feature in the problem, so I do want to mention it. But I know I probably lost you at it's not in the test, is how scale factor extends to volume. So if I have a shape, whatever it may be, could be some sort of rectangular prism perhaps, some sort of box or whatever. And let's suppose the original had, let's say here, a 2 centimeter by 1 centimeter base, and the height was maybe 3 centimeters. So the original volume, my writing is not very good today, is area of the base, 2 centimeters by 1 centimeter times the height, so 3 centimeters. So I get 6 cubic centimeters. Oh, not that. Funny. 6 cubic centimeters. That's the volume of the box. If I now say we increase all the side lengths, all the sides, by a scale factor, let's say k, let's say 50%, so 1.5. That looks like a 6. 1.5. What is the effect on the volume? Well, remember that the area factor was k squared. So surface area or just area of a two-dimensional shape or whatever would be scaled by this factor. Because the two, if I look at the area of the base here, for example, the two lengths feature multiplicatively to get the area of that rectangle. So a k times a k features. Now the volume adjustment is similar, except the volume factor, if we'll call it that, is going to be k cubed because I have 3 dimensions. Each one is scaled by this k. So if all sides are scaled up by a factor of 1.5, then the new volume is going to be k cubed times the original volume. So that is going to be 1.5 cubed times 6 cubic centimeters, and we get a new volume of 20.25 cubic centimeters. So I'm not making a big deal of this because we've already done those things in area, and when it comes to volume, everything is exactly the same, except instead of k squared, it's just k cubed because I have that extra dimension. So you might see problems at the end of this chapter referring to a scale factor. Uh, just know that that is the only adjustment that we need to make. If I change the side lengths by a percentage or a factor, then that appears sort of 3 times multiplicatively in its effect on the volume. Any questions on scale factor and how it extends to volume? I know I shouldn't have led with it's not going to be on any test. Now you've stopped listening. That's totally my fault. I never learn. I never learn.
I'm still listening, still here.
All right, good, good. So the last little bit when it comes to volume is just how the circle extends. Ooh, we do have space. Very nice. So we have 3 dimensions, right? We have the length dimension, we have the area dimension, if I'll call it that, and then we have volume. 1 dimension, 2 dimensions, 3 dimensions. When it comes to a circle, we have the concept of circumference. Whoops. For a circle with radius r, 2 pi r. So there's my circle here. Radius r. And then we have area, pi r squared. And we saw an argument, medium level of formality, not super fancy, but still mathy, for where the area of a circle can come from by way of approximating it with an inscribed irregular polygon. And then we have the, let's say here, area of a circle, circumference of a circle. And for 3 dimensions, we have the volume. My writing is too sloppy. Volume of a sphere. Now, drawing a sphere, I just do something like this. And then maybe a little line here indicating it's 3 dimensions. Something like that, I don't know. Still radius, r. The volume of a sphere, you can take a similar approach to our argument to get to the area of a circle. It's just a little bit fancier because we have this extra dimension, and we get a volume of 4 over 3 pi r cubed. The y is something that is just a little bit more complicated, but it can follow a similar idea, inscribing a polygon and then letting the size of the polygon inside the circle get bigger and bigger and bigger. It approaches the circle, and the approximation gets better and better and better. Here, all I need to do is look at an inscribed regular polyhedron and let the number of sides of that, in a way, there are faces as well, increase, getting a better and better approximation of the cube. But then I need volume formulas for all of that, which I'm trying to avoid, since they're never going to come up for you ever again. But the concept is very similar. However, in 3 dimensions, I also have surface area for the sphere of a sphere. And these are just formulas that I have to remember. With some calculus, you can prove these things quite easily. It's going to be 4 pi r squared. So if r is like a centimeter unit, I see here I get a centimeter unit. Here I get square centimeters. And here I get cubic centimeters, for example. And here I'll get a square centimeters again, because it's an area. It's the outside area of the circle. So I just have to remember, do it over and over. Volume is 4 over 3 pi r cubed. Surface area is 4 pi r squared. Whatever works for you for how to remember that. And then we can calculate. I'm not sure if I have an example.
Hey, Steven.
Yes.
Um, Where's that 4/3 for 4/3 pi r cube comes from?
Uh, it comes from an argument that's similar, well, one of the ways, an argument that's similar to what we did to get to the area of a circle formula. You have to extend that argument to 3 dimensions, and then what comes out is 4/3 pi r cubed. The simplest derivation of that formula is perhaps using calculus. It's quite straightforward, but we need calculus, which is not the focus. So we can't really justify where that formula comes from. We're just going to have to remember it.
Okay, so it's kind of a just because kind of thing.
Well, for our level, yes. But in terms of the grand mathematical scheme, it's not a totally difficult one to prove. We just don't have all the tools to make sense of it, and we don't need to either. So if little Timmy ever asks you, why is it 4/3? Yeah, that's a tough one. He just doesn't have the concept to understand why it is. Yeah, unfortunately.
Okay, thanks.
You can think of it as if we extended this inscribed polygon concept to an inscribed polyhedron inside the sphere, that same approximation, improvement concept and argument would work. The formulas are just messier. All right, so if we, I don't think, did I check? I missed my bar. My bar is at the side here. Oh, that's interesting. Oh, I don't think I have even a, I got lazy at the end here, I think, in this draft. You can easily just make up a sphere and we can calculate the volume and surface area just to be sure. So let's take a sphere of radius. Let's make it, I don't know, 3 centimeters. Maybe not 3. Yeah, sure, 3. Why not? So then the volume is 4/3 times pi times 3 cubed for the radius. We'll get an answer. Surface area is 4 pi, whoopsie, ugly pi, there we go, times the radius squared, and we get an answer. So let's see those two. For the first one, I get 113 point, if I round it to 2 decimal places, 10. For the surface area, now oh, that's a terrible example. Terrible. I need to go back. This is a horrible example.
Why is it horrible?
I picked the one radius where the volume and surface area are the same. And then it gives people a false impression that these two things, oh, they're always the same then, I guess. I just picked a terrible radius. Let's pick something else. Let's pick a 5. There we go. I know it happened yesterday as well. Subconsciously, I'm doing this on purpose. I'm sure. I am sure. So redo volume with a 5 centimeter radius. And we get 523.6 if I round it to 2 decimal places. surface area. Much better. 314.16. So let's get those units in there. Volume is cubic centimeters. Surface area is square centimeters. And that's pretty much it for the sphere. So in terms of volume, we have a prism concept where the base could be anything, something I can calculate the area of, and the sphere. And then surface area, we have our basic polygons featuring as surface faces of a three-dimensional shape, but we also have the sphere, which has its own surface area formula. And that is the end. Now, there are a whole bunch of problems, so we'll certainly go through what is on the quiz again and what especially is on page 5 and which problems we need to focus on. But in terms of the material, we have finally arrived at the end. No more formulas. But even honestly, even if uh, we have a whole bunch of formulas, our situation now is better that at least we have an open book test this time. So there's no memorization. I'll just end the video, the YouTube video, before we talk about quiz and problems specifically.